Hi, Mr. Green here. I'm going to take you through another section of the electricity part of the AQA Physics GCSE. This is on the national grid, and the learning objective is to know how the national grid supplies our homes with electricity. Please pause the video and get that down as your title. Okay, first thing is a retrieval practice to start with. Please pause the video and attempt those 5 questions. Restart when you would like those answers. Okay, question 1. What are the 3 wires and the colours in the UK plug? We've got live, which is brown, neutral, which is blue, and earth, which is green and yellow. So banded green and yellow. Question 2. What's the voltage supplied by UK mains electricity? That's 230 volts. Question 3. What frequency is UK mains electricity supplied at? That's 50 Hz. Question 4. What's meant by alternating current? Alternating current is a supply where the current is constantly changing direction. That's why it has a frequency of 50 Hz. It changes direction 50 times a second. And question 5. Give an example of a device that supplies direct current. We're talking about a cell, a battery, which is a series of cells together, or a dynamo. Okay, please pause the video to check you've got those answers right. If not, please correct them and green pen your answers that you've got correct. Okay, so our learning outcomes today are to describe the national grid and to state the functions of the transformers in the national grid. For our starter, we're going to have a look at these because it's going to be just a look at how safety in electricity is concerned. What's the issue with each one of these plugs? So pause the video, have a look at each plug and tell me what the issue is. Okay, so the first plug, top left-hand corner, you'll see that the banded green and yellow wire, the earth wire, is at the top, but the neutral wire is in the pin on the right, and the live wire, which is brown, on the left. They're the wrong way round. So that if you wired up that appliance, that wouldn't work, and that would be dangerous to set it up that way. The second one on the top, you can see there's bare wires exposed in the plug. Though that insulation, the coloured blue, brown and green and yellow, should go all the way to the ends of those wires. So that would be a dangerous plug to use. It could cause an electric shock. As would the one on the top right hand side. There's no back cover to the plug exposing those wires. So again, it's not one that you should use. Bottom left, this plug here is cracked and it's exposing part of the inside of the plug. Again, dangerous to use because that part of the plug shouldn't be shown. It could cause an electric shock. And bottom right, you'll see that coin in the middle there is connecting all 3 pins together. So that's going to cause a short circuit. It would rather flow through the penny than the appliance itself, and so that could be dangerous again. Anything like that with any appliances that you're using, do not use those appliances. Do not plug them in. They will be dangerous to you to use. Okay, so the national grid. Essentially, it's a nationwide network of cables and transformers. The national grid, you can see there a power station on there, and that's where the electricity is generated in power stations. We can use oil, coal, natural gas to generate those, or we can use some renewable resources. There are videos to watch on our YouTube site that will take you through those. But essentially, they generate the electricity, but that then has to get to you, the consumer. So the national grid is the way that electricity gets from these power stations to us. The beauty of the national grid is that electrical power generated in one part of the UK can be used anywhere else in the UK. We don't have a local power station that only supplies us. Our local power station will supply us and the rest of the UK if they need it. It all joins together and all connects up. So if our power station has to go down for maintenance or any sort of service, it doesn't mean our electricity supply stops. It means that we would then divert electrical power from another power station, they would up their output and it would supply us. National grid wires are coiled together to form larger wires that we call cables. Now these cables are held above the ground and some cables are buried underground. Cables are held above the ground because, again, they're carrying electricity at extremely high voltage, and they would be dangerous if we got in touch with them. We wouldn't want them to interfere with anyone on the ground. We wouldn't want us to touch them and get ill and get an electric shock from them. And again, for the same reason, some cables are buried underground to keep them away from people, to keep them away from animals, to make sure no one gets injured by them. Here's why some are buried underground. Let's see this area here. We've got an electrical appliance there. We've got electrical wires carrying there, and they've got loads and loads of ice on there. Now, if that ice continues on, and if it continues to get more and more ice on there, this could happen. Or this, which makes it even more dangerous. So in areas where there's lots of cold weather and there's lots of frost and lots of snow, places like Sweden, they will bury those electrical cables underground to prevent this from happening. Okay, quick progress check. Pause the video and attempt those 5 questions. Start it again when you'd like me to go through the answers. Okay, question 1. What's the national grid? National grid can be described as a series of cables, power stations and transformers stretched across the country. Question 2. Where is electricity generated? It's generated in power stations from coal, oil, natural gas. We have nuclear power stations and renewable power stations as well. How does this pass to households and businesses? Through electricity cables that are connected to the power stations. We're going to look at exactly how that's done in a minute. Question 4. Why are cables high overhead and buried underground? It's safety, so people and animals can't touch them and get a shock. And 5. Where would cables be buried underground rather than above ground? That would be in cold places. Ice can cause the cable to get heavy and cause pylons to collapse, so anywhere where it's generally very cold for a large portion of the year, they would bury those underground to stop them getting ice on them. Okay, power stations generally produce electricity at 25,000 volts. Now when that's sent through the cables of the national grid, that electricity is then at 132 to 400,000 volts. So any pylons that you see, any wires that you see above you, that's the size of the voltage going through those wires. Now when that arrives in our homes, that's at 230 volts. So what do you notice from there? Note down what you've noticed from what I've just told you. You should be able to see that at each point the voltage changes. So we need to know, 1, how does the voltage change? And 2, why does the voltage change? Step up and step down transformers do this job. They will change the voltage of the electricity, and they do it for a very important reason. Step up transformers increase the potential difference between power stations and cables in the national grid. Steps it up from 25,000 to 400,000. Step down transformers do the opposite. They decrease the potential difference from 400,000 in the national grid to 230 in our homes. Now it does it for this reason. When a current flows through a wire, some of the energy is lost as heat. The higher the current, the greater the energy loss. So we use a low current to transmit electricity around the national grid. If we want a low current, we have to have a high voltage. So to ensure we don't lose lots and lots of energy as heat through the national grid, we transfer that at a low current. In order to get a low current, we need a high voltage. So before it goes into the national grid, into those cables, we go through a step-up transformer, increase the voltage really, really high, make sure that current's low so we lose less energy through heat. Now this is known as a power station because that's what it does, it produces power. Cables suspended from pylons are known as power lines because they transmit power. So increasing the voltage reduces the current. The smaller the current, the lower the loss of power. Electricity is moved through the national grid. So power stations generate power, the power cables will transmit the power. To ensure we don't lose power, we put the voltage as high as possible so that we don't lose energy through heat, so the power remains as high as possible. This allows precious energy resources like oil and gas to be converted much more efficiently into electrical energy. There's much less waste and much less cost to the consumer. But if we were to put that electricity into your home at 400,000 volts, 225,000 volts, it's much too high for us. So what it does before it gets to you is goes through a step down transformer which changes that voltage to 230 volts, which is perfect for us to use. Okay, here's a diagram showing the national grid. Pause that, and at each point, A, B, C, D, E, F, G, H, and I, you can put one of the words that's at the top. They will fit in there. So write down A, B, C, D, E, F, G, H, I, put the answer that you think is there, unpause the video, and I'll go through those answers for us. Okay, so for A, we should have written the power station. B, 25,000 volts. C is the step-up transformer. D, the power lines. E, that's got electricity at 275,000 volts. F, that's your pylon. G, well, if C was a step-up transformer, G is a step-down transformer. Step-down transformers give us electricity at H, 230 volts, and that's supplied to our homes. Okay, quick progress check. Pause the video and answer those 3 questions. Restart when you'd like me to give you the answers. Okay, so question 4. Why is the voltage very high in the cables? It's to reduce energy waste. Very high voltages produce less heat in the cables. So very low voltages will produce large amounts of heat because the current's so high. Question 5. What type of transformer is used to reduce the voltage before it's supplied to homes? That would be a step-down transformer. And question 6. The electricity companies supply thousands of homes with electricity through the national grid. Why might some people be unhappy with the electricity suppliers building power stations near their homes? You need to think about the inconvenience that would be caused if someone built a power station near your home here. So there'd be large volumes of traffic. There would be dangerous electrical cabling all around the area. There would be visual pollution because it looks bad, and there would be air pollution from them burning those fossil fuels. So that's one of the many reasons people would not like power stations to be built near their homes, and one of the many reasons power stations are built in areas where there's not much residential area there at all. Okay, to finish off, we've got multiple choice questions. 4 questions there. Pause the video, have a look at those, restart, and I'll give you the answers. Okay, question 1. Complete the sentence. The national grid is a... Correct answer there would be A, a series of cables, pylons and transformers. Question 2. What do step-up transformers do? Again, step-up transformers would increase the voltage, which would A, decrease the current. Question 3. How do we reduce the power wasted when electricity is carried through cables? Correct answer is B, we'd increase the current so less heat is lost. And finally, question 4. Why do we need step-down transformers? It's so electricity enters our homes at a safe voltage. Again, hope that one was useful to you. Please review the video again if you'd like to know more about it. And we've got lots and lots of videos available on our YouTube channel. Hope you found it useful. Thanks very much. Goodbye.